Okay, this is the notes for 8.3, constructing a confidence interval for a population mean now instead of a proportion before. So the formula is similar as long as we know the standard deviation of the population. It is this, so a level C, so let's write this first. As long as the conditions are met, so I'll just write it like this, as long as, I'll just write it as RNI, random, normal, independent. A level C confidence interval. Confidence interval for population mean mu is the sample mean x bar plus or minus z star, and z star comes from is your standard normal critical value depending on your confidence level. So plus or minus z star, and then for mean you have standard population standard deviation over the square root of n, where n is your sample size. And so when we if we're given the certain margin of error, plus or minus a certain margin of error, we want to find the sample size n, we're just going to set this part equal to the margin of error and solve for n. It works just like with proportions. And we'll do an example in a little bit. But here's the thing that makes the mean more interesting. So, and we're going to use a whole different kind of distribution here. When the population standard deviation is unknown, which is more typical, is unknown, then we can't use this if we don't know what standard deviation is. So when it's unknown, we're going to use a t distribution. And it's better illustrated with videos, but a t distribution looks just like a normal distribution, except the tails are fatter. And so we'll see some videos on that. But you'll use a t distribution, and you'll use a different table as well. So the formula for that, we still have to check our three conditions. So I'll write that again. As long as RNI, then our confidence interval would be computed using this formula. It would be x bar, sample mean, plus or minus t star, which I'll show you how to find using the tables in a minute, t star, and then since we don't know the population standard deviation, we use the sample standard deviation, which we can calculate because we took the sample. So that's notated by s sub x over the square root of n, where n is the sample size. So this part here is called the standard error of the sample mean. Standard error of the sample mean. Sample mean. And you compute and s sub x in this formula. S sub x is the sample standard deviation. Sample standard deviation in the formula, and t star comes from table B, which I'll show you when we do the example. Comes from table B. When you use a t distribution, you use table B rather than table A. Comes from table B, and when you look things up in table B, you have to use, instead of the sample size n, you use what's called, it's a weird name for it, but it's called degrees of freedom. degrees of freedom. I don't know why it's called that. So degrees of freedom, df, and all you need to know is that it's equal to 1 minus the sample size. It's just n minus 1. And you'll see that it's easy when we do the example. But the degrees of freedom is n minus 1. And you'll see in the video as the degrees of freedom increase, in other words, as the sample size increases, the t distribution will approach a normal shape. But again, easier to see in a video. So those are the formulas, but there's one caveat here. When you check the normal condition to use this test here, when you check, so like caveat, normal condition, the random and the independent, you do the same. But for the normal condition, for using this test, this formula, for using, and the formula is called one sample t procedure. Everything's one sample for now. One sample t procedure is this. When you're checking that one condition, the normal condition, it's okay to use this procedure. So okay if the population distribution was already normal to begin with. You would have to be told that. Okay if population, it's okay to use this if population distribution is normal to begin with. Distribution is normal, or, and you're familiar with this too, or because of the central limit theorem, which just works for means, by the way, not for proportions, or sample size n greater than equal to 30 because of the central limit theorem. You're fine. You can use this procedure, but it's also okay. So central limit theorem, I'm going to switch. If sample size n greater than equal to 30 because of the central limit theorem, or if your sample size is less than 30, now you get to use what we learned in chapter 1. You have to actually look at the data. So normally we would say if sample size less than 30, we can't use this procedure, but it's still, if n less than 30, okay, if you look at the data, so even if you only have a sample size of like 10, it's okay if data is close to normal, which you would figure out by graphing it. Close to normal, meaning it's roughly symmetric, no outliers, and no strong skewness, then we can still use this procedure, and we'll see that in one of the examples in a minute.